Hello there people. Let's now see these two questions. One is from GATE 2004, other one is from GATE 2012. Both are 1 mark questions. First we are going to see the question from 2012. I'll read out its statement. It says, the amount of ROM needed to implement a 4-bit multiplier is. Okay. First thing you need to know, when we multiply two 4-bit numbers, 4-bit multiplied by a 4-bit number will result into a 8-bit number. That means the result could need 8 bits maximum. For example, the biggest 4-bit number is 15. Here also the biggest number possible is 15. You multiply these two and surely the result will be of 8 bits. Okay, the result could need maximum of 8 bits. Anyways, the result can also be represented in 1 bit. If your first number is 0, second number is also 0, then the result is 0. You can represent it 0 in 1 bit. What I am trying to say is, in worst case, the result will need 8 bits. That is 4 plus 4. So you can see n-bit number, when multiplied by n-bit number, it might require 2n bits in some cases. N-bit multiplied by n-bit could consume 2n bits. Okay. Now let's see how much ROM will be required to implement a 4-bit multiplier. First, understand the question. We don't want to multiply any two 4-bit numbers. We actually are saving the result beforehand. What's happening is we are not calculating anything. We are not even using the CPU. It's a ROM memory, that is read-only memory. Say this is your memory. First thing is, because we are saving a result which could be of 8 bits maximum, that means each location has to be of 8 bits. Okay. Let's go slow. Say this is a memory where each location is of 8 bits. What we are doing is we are saving 0 multiplied by 0 here, then 0 multiplied by 1 here, 0 multiplied by 2 here, and so on. So in total, how many such combinations do we have to save? This is 2 power 4 combinations. The first number could generate 2 power 4 possible numbers, or first number could take 2 power 4 values, which is from 0 to 15. Okay, so these are 16, which is 2 power 4. Parallelly, the second number could also take 2 power 4 values. So when we pick one number from these 2 power 4 and other number from these 2 power 4, in total you are going to have 2 power 8 combinations in the input. So what has happened is, you have a ROM in which one location is of this size, 8 bits, and in total you have 2 power 8 locations. So what is the total size of ROM? So the total size comes out to be 2 power 8, these many locations, into size of one location. Okay. So this is 2 power 8 bytes. Let's see the answer. What is it? Okay. So we need not calculate the answer in bytes because the question, or rather the options, only have bits. Let's keep it as it is in bits. This is 2 power 8. This is 2 power 3. So total becomes 2 power 11. The unit is same, i.e. the bits. 2 power 11 means 2k and bits is as it is. So your answer is 2k bits, which is option D. Okay. So the answer to this question is option D, 2k bits. 2 power 11 is written as 2 power 10 into 2. This 2 remains as it is. 2 power 10 is replaced by 1k because 1k is actually 2 power 10. Okay, so the answer here is 2k bits. I'll just explain this concept once more for my satisfaction. What has happened is, you know that one location has to be of 8 bits because the product could be maximum of 8 bits. In worst case, the product might require 8 bits. Okay, and what is this? This is the first number, this is the second number. Every possible combination of these two numbers has been counted. Okay, so these locations contain the products. For example, this last location will be 15 into 15. The product is going to be 225. So here we will be saving 225. These are the actual answers. We need not use our CPU here. Okay. Now let's see a similar question from 2004. Yeah. What is the minimum size of ROM required to store complete truth table of an 8 bit cross 8 bit multiplier? That means now you are saving all the products of 8 bits into 8 bits. That means this size is going to be 16 because n now is 8. N cross n is 2n. Okay. It's actually n bits. N bits cross n bits is 2n bits. So here this value will be 16. So our product could be of 16 bits in worst case. That means each location has to contain a 16-bit value. So this is 16. We just need to find this much. This will also be 2 power 16. How? Because the first number is of 8 bits. Okay. Second number is of 8 bits again. And if we place these two numbers next to each other, that means if we see this one number as a whole, you'll see these are 8 bits, these are 8 bits. In total, they are 16 bits. So the input could have 2 raised to the power 16 combinations. How did I get that? You see, this is 0 times 1. In the previous question, it was a 4-bit number. This 0 is a 4-bit number and 1 was also 4-bit numbers. Writing 0 in 4 bits and 1 in 4 bits, we get this. Now this could be used as an address. To address this ROM, you just place first number and second number side by side and use this entire bit pattern as an address. So this column, this is 0th, this is first, this first one gets that address, which actually is 1. Okay, so similarly 0 cross 3 will going to get an address which is 0 in 4 bits and 3 in 4 bits. Now this value is actually 3. Okay. So here what will happen is this is 8 bits, this is 8 bits, they are placed adjacent to each other and in total we get 16, 2 raised to the power 16 addresses or input combinations. That means this is 16, 2 raised to the power 16 and one location is of 16 bits. So your answer is going to be 2 raised to the 16 into 16 bits. Let me see what's the unit according to the options. Okay, here also we need not convert into bytes. And your answer is option number B. How did I get option number B? It's 64K. So this 2 power 16 can be written 2 power 10 into 2 power 6. 2 power 10 becomes K. This is K. And 2 power 6 becomes 64. 64K and these 16 bits are copied as it is. This is your answer, which is option number B. Now you might ask, why have we left 16 bits as it is? It's a convention that this represents the total number of locations. That means the number of locations that we have in RAM. And this represents size of one location. Okay, so that's the reason why we have left answer like that only. We could also multiply it. You could also say the answer is 2 power 16 into this 16 is 2 power 4. So 2 power 16 into 2 power 4 is 2 power 20. You can simply say it has 2 power 20 bits. Okay. Anyways, this is not a theoretical exam. You need to mark this answer only. It's an MCQ type of question. Okay. So anything that I've left? Yeah, if you need to know more about these memories, these ROM memories or RAM memories, you can watch my lectures on memory organization as well as memory implementation. I've explained this in great detail where I've discussed PLDs, programmable logic devices. So I've explained ROMs, PLAs, PALs, etc. in this video. Okay. Thank you very much for watching this one. I hope to see you in the next lecture also.